Okay, this is Calculus Lesson 4.2. It's about Riemann sums and area, and we're in the integration chapter, so some of these terms are going to be new, and you may wonder at first what this is all about, but it's all going to come together very shortly in probably one more lesson. A Riemann sums are just named after, I believe his name was Georg Riemann, and he's just the one who came up with the idea of adding up shapes underneath curves to estimate areas. So we're actually going to be estimating areas. So here's what the problem would look like. We're going to estimate the area bounded by the curve and the x-axis. And what we're going to do is we're going to do three types of sums. We're going to do a left Riemann sum, a right Riemann sum, and a midpoint sum. If you printed out the notes page, then you'll notice there's also a trapezoid rule after that. So this is actually very geometric. We would start off by writing the problem. So the example we're going to use, y equals the square root of x. It's on a closed interval from 0 to 1. N equals 4 subintervals. All that tells me is how many shapes do I break it into. And Riemann sums are always going to be rectangles. So I usually tell students to remember Riemann starts with an R, rectangle starts with an R, so a Riemann sum is a rectangle. So what we're going to do first, I've drawn my picture and I've labeled it. And the subintervals are going to basically tell me from 0 to 1, I'm breaking it up into 4 parts. So you can see my 4 parts, even though it's probably not beautiful. Now the first thing we're going to do is called a left Riemann sum. I believe that's right. Let's see. Yes. So when we do a left Riemann sum, what we're going to do is we're going to pick the left endpoint of an interval, and we're going to draw a horizontal line. So left endpoint, horizontal line. Left endpoint, horizontal, left endpoint. Oops. Let's try that again. Left endpoint, horizontal. Okay, so as you can see, the first rectangle I've made is flat. It has 0 area. But we can do an area for this rectangle, we can do an area for this rectangle, and we can do an area for this rectangle. And if we add them all up, then we have an estimate for the area. Now, if you were in class talking to me, I would say, does this look like a good area? And you would probably say, no, that doesn't look like a good estimate of our area. But considering how small our interval is, it's really not going to be too bad. So let's start off by setting this up. How do you set up a left Riemann sum? Well, we're talking about area, and Riemann means rectangle, so we're talking about length times width. So basically, I would do the length and the width of each rectangle. So my first one has a length of 0 and a width of 1/4. My second little thing has a length of, let's see, how high is this rectangle? It's 1/2. So 1/2 times 1/4. The next one has the height of 0.707, which is actually the square root of 1/2 times 1/4. And the last rectangle is actually going to be the square root of 3/4 times 1/4 as I run out of space. Okay, so we have 4 rectangles because we have 4 subintervals. So I work this out. I have 0 plus 1/8 plus 1/4 times the square root of 1/2 plus 1/4 times the square root of 3/4. Put this in your calculator. Put a little squiggly on there because we're estimating. And when we did the left Riemann sum, we get approximately 0.518. Okay? So approximate area under that curve, between the curve and the x-axis, is 0.518 units. Squared, I guess, because it's area. Okay. Now, same picture, same values, but this time we're going to do a right Riemann sum. So let's switch to a different color. I still have my subintervals like this. I'm still talking about rectangles, but if I talk about a right Riemann sum, I start with the right endpoint and draw my horizontal. Right draws horizontal. Right draws horizontal. And right draws horizontal. And notice that since I'm above the curve, I'm having to draw it down to complete my rectangle. So now look, see how much over this is going to be? This is an overestimate. When we did the left Riemann sum, it was an underestimate because we had all this extra that we didn't get. Okay? So hopefully you're kind of getting the idea. We're using rectangles, but we're approximating, and so this one's going to be an overestimate. So if I did the area, now I'm going to do a little bit of a shortcut. I know that this width is 1/4, this width is 1/4, this width is 1/4, and this width is 1/4. So I'm going to put the 1/4 out front, and then I'm going to add up each of my lengths. So I have the square root of a 1/4, plus the square root of a 1/2, plus the square root of 3/4, plus the square root of 1. And the reason it's the square root is because, remember, this graph is y equals the square root of x. So whatever my x is, the y value is its square root. Okay, and I went ahead and did this in the calculator, and now I've got my little squigglies going because it's an estimate. And this estimate was 0.768. 0.768. Okay, so that's definitely an overestimate. And the last estimate we had was 0.518, which is definitely an underestimate. So it does tell us the actual area is somewhere between those two. We know it's definitely not bigger than this, and it's definitely not smaller than the left Riemann sum. All right, but could we do a better estimate? Probably. What would be a good way to do a better estimate? This is called a midpoint. So the midpoint is going to put more dots on my picture. I'm going to put a midpoint at each one of these, okay? And then I have to label them. This is 1/8, this is 3/8, this is 5/8, and this is 7/8. So how is this going to work? Well, we're still going to have our same intervals. We have 4 even intervals. But this time I'm going to go from that midpoint, and I'm going to draw the horizontal through the midpoint and connect it, horizontal and connect it, horizontal and connect it. So this height is going to be based off of the 1/8. This height is based off of the 3/8. This height is based off of the 5/8. This height is based off of the 7/8. So what you might notice is that there's almost the same amount of over area as there is under area. So it kind of balances out. So is the midpoint Riemann sum going to be a little bit better of an estimate? And the answer for that is yes, it should definitely be a better estimate. So I'm still talking about length times width, and all of my widths are still 1/4. That has not changed. So I've got 1/4 times, and I'm going to do each of these heights as my length, okay? So we've got the square root of 1/8 plus the square root of 3/8 plus the square root of 5/8 plus the square root of 7/8. And in case you have forgotten, remember our equation is y equals the square root of x. So when we have 1/8 here, its y value is the square root of 1/8, and the square root of 3/8 is the square root of 3/8, and so forth. So put this in your calculator, put a little squiggly in there, and you get 0.673. Now, the midpoint estimate is a much better estimate, no doubt about that. The only problem with the midpoint estimate is we don't really know if it's above or if it's below. We just know it's definitely closer. Okay. So all of these are estimates, and these are all Riemann sums that we've tried so far. The last thing we're going to look at is called the trapezoid rule. All right, so you might have noticed the left Riemann sum and the right Riemann sum were either over or under quite a bit. The midpoint really tried to balance that out, and the trapezoid rule is an idea that really, really does a good job of balancing out how much is left over. So when you do the trapezoid rule, you take all your endpoints and you connect them. And so you can tell that this is all a little tiny bit under, although my drawing's not great, but it's a little tiny bit under. So whatever we get with the trapezoid rule, not only is it going to be closer, we know that it's a tiny bit under, so we don't have to wonder if we got a good answer that's over or under. We're going to be really, really close to what the actual area is. And in lesson 4.3, you're going to learn how to actually find that area. Okay, so how does the trapezoid rule work? Well, you just have to know the area of a trapezoid, which is 1/2 h times b1 plus b2. All right, so the problem is your h is going to be this way. And so when I do b1 and b2, I have b1 here and I have b2 here for my first trapezoid, which you may notice is not a trapezoid, it's actually a triangle. The second trapezoid, this is going to be base 1 and this is going to be base 2. The third trapezoid, this is going to be base 1 and this is going to be base 2. And for the fourth trapezoid, this will be base 1 and this will be base 2. Sorry, base 2. Okay, so let me show you how that's going to look then. So again, the area of a trapezoid, I'm just going to put it all together. So I'm going to have 1/2 the height. Every one of my trapezoids has the same height, and it's the same as the width from the rectangles. They're all 1/4 because we did 4 equal subintervals. So I'm going to leave that part on the outside. And we're going to do the first trapezoid base 1 plus base 2. So that's actually the square root of 0 plus the square root of 1/4. The second trapezoid would be the square root of 1/4 plus the square root of 1/2. The third trapezoid would be the square root of 1/2 plus the square root of 3/4. I'm obviously running out of space here, plus the fourth trapezoid, which would be the square root of 3/4 plus the square root of 1. So I'm going to take that bracket right there away and put it down here. Okay, so let me simplify this for you a little bit. I have 1/8 times 0 plus the square root of 1/4 plus the square root of 1/4 plus the square root of 1/2 plus the square root of 1/2 plus the square root of 3/4 plus the square root of 3/4 plus the square root of 1. So I have 2 of these, I have 2 of these, I have 2 of these, I have 1 of those, and we had 1 0 also. Alright, so put it in your calculator. Round it to 3 decimals. That's going to give me 0.643. So now that we've seen all of our examples, our midpoint Riemann sum gave us 0.673 as an answer, so we know it was an overestimate because the trapezoid rule is always a little bit underneath because of the way it connects the dots. So, I forgot to put squigglies. So we can conclude that the area under the curve of y equals the square root of x, the area between that curve and the x-axis from 0 to 1 is approximately 0.643 units squared. Okay? You have a worksheet that goes with this that you can pick up in class.